right, thanks, Barb. And yeah, we'll move on and hear now from Jeff Seawald, also from WHOI.
So thanks, Barb. That was really a great framing of the task at hand. So I'm from an oceanographic background, so I'm learning. Turn that on. Examples of what we consider abiotic processes in submarine hydrothermal systems, and considering their sort of central role that they're believed to play in making ocean worlds habitable, perhaps we can learn something from studying these systems on Earth. And looking at these abiotic processes in an Earth environment, ever since the discovery of hydrothermal activity in submarine environments, there's been this sort of interest on what sort of abiotic carbon chemistry can be occurring in these environments. And the interest stems from really the same reasons that we're all interested in planetary science and other ocean worlds. But there's a little twist. We know that biology is existing in these systems. So one of the other aspects that we worry about is when we typically will go look at vent fluids at the seafloor. Quite often we're trying to understand the role of biology in influencing the chemistry of these fluids. In order for us to do that, we actually need to know what's going on abiotically in these systems. And then we have all the other reasons of interest. Making reduced carbon compounds is a source of metabolic energy for for organisms living in these environments. And then we also can use the abundance and isotopic composition of reduced carbon compounds to actually tell us a little bit about what's happening in subsurface environments. So I'm going to take you a few case studies of different environments, different physical and chemical conditions. And one of the points, this is my attempt to make the point that old Chris really made nicely at the end of yesterday, that hydrothermal activity on Earth's ocean occurs in a range of environments, over a range of temperatures, a range of depths, a range of rock types. There's a lot of water flowing through the ocean crust. And so we're dealing with a huge range of systems and potentially a range of processes that can actually result in abiotic synthesis or abiotic reactions. Don't worry about the details of this slide. What I'm showing here are the range of concentrations of hydrogen that we've measured in all those environments that Chris talked about and were in the previous slide. These are hydrogen concentrations and dissolved sulfide concentrations. And one of the common features of all these systems is they're all very reducing, regardless of over a range of rock types, a range of temperatures. And so there's a potential. We hear a lot about ultramafic systems, but there's also a huge potential in a lot of these other systems, in mafic hosted systems, and even in back arc environments where we start dealing with more felsic rocks. So chemically, these systems are primed for a lot of these reactions. And those of you who perhaps care about carbon monoxide, this is just a plot showing there's not a lot of data for carbon monoxide, but it's a good feedstock for synthesis reactions. This is just for the data we do have. We can predict the concentration we would expect based on the carbon dioxide and the hydrogen that we see in these environments. And it's always present at equilibrium. So carbon monoxide is also expected to be abundantly, or not abundantly present, but available for reactions in these systems. This is the water gas shift reaction. It's very fast in hydrothermal systems. So Barbara gave some definitions. We thought when we were putting these coordinating lists, I would take on these definitions. You've heard some of these, I think, in some of the previous talks, but just define some of the types of organic matter that I'll be talking about, and I think you'll hear about in some of the talks later today. We use this term insoluble organic matter, and it's just sort of like it sounds. It's the residual solid organic matter that's not soluble in most common organic solvents. I think everyone has their favorite solvent, but typically it's the solid material that remains. Macromolecular organic matter, Frank did a really good job. It's these large, sometimes complex molecules. Kerogen is the term we use on Earth to describe macromolecular material, but it differs from meteorites in that it's composed of the remains of once living organisms. And then I want to talk, just this is a minor point, but you often hear the term volatile compounds. Keep in mind when we're talking about hydrothermal systems, quite often they're actually not in the gas phase, they're actually dissolved in water, and we're dealing with aqueous species. Barbara did a really nice job describing that the isotope signature alone is really not a smoking gun. And if you look at the literature, these are a couple of more criteria that you'll quite often see to identify abiotic compounds on Earth. And this is sort of tailored a little bit more towards hydrocarbons. But the reason I included this is that there's no smoking gun. There's not one thing you can say, oh, this is abiotic. And so it's multiple things that we're looking at, typically the geochemical and geological context, as Barbara mentioned, really important. And so when you put all this information together, then you can actually make an assessment as to whether we're actually looking at something abiotic. And again, we have this issue that biology contaminates everything, right? Unlike abiotic signatures, though, on Earth, we do have a smoking gun for biological. You can actually see cells, so quite often you really know that there's biology involved. Sometimes it can be unclear when you start getting into thermogenic products, which is a little ambiguous. But anyway, the point here is we're looking at multiple chemical and geological contexts to make these types of assessments. Chris showed this vent yesterday. This is the Aurora vent field under the ice in the Arctic. And I wanted to draw your attention. So here we have sort of a high temperature black smoker. We've all seen these before. But if you look down here, you can see these low temperature fluids that are venting. And so right in this very small spatial area, we have two very different chemical systems. This is about, these are about 120 degrees. So these low temperature fluids are formed by the high temperature fluid mixing with seawater below the seafloor. So you start with the chemistry of this high temperature system, and you can see that these are clear, it's lost all its metals, but there's a lot of chemistry. So we can look at these two environments, and I'm going to give you two examples of different types of processes, sources of abiotic compounds, some affecting the high temperature system, some affecting the low temperature system. And they're not only are they occurring over different temperatures and chemical environments, they're also occurring potentially over different time scales, which is really important. So I thought I would start with the methane and some low molecular weight hydrocarbons. And these are data from ultramafic influenced systems on the seafloor. And what you'll notice is that this is methane, ethane, and propane. In terms of concentration, they show these very similar trends in terms of their relative abundance over a range of systems. And what's really interesting is that these are very, very different systems. We have the Lost City system. It's a very low temperature system, pH of 10.5. You have high temperature Rainbow, 365 degrees, very acidic. We have the Von Dam system, intermediate temperature, near neutral. Yet you see the same relative abundance, and I realize this is a log scale, but the actual absolute abundance is not that different between all these systems either. And if you look at the isotopic composition, they also show a fairly narrow range of carbon isotopes. And when this suggests to me that there's a common process that's forming these hydrocarbons in these systems. regardless of the chemical environment of the actual vent fluids. Other interesting aspects of the fluids, we can look at the abundance of CO2 and the radiocarbon. I'll get to that in a minute. But the general idea, the conventional wisdom early on in the hydrothermal world was that multiple people have talked about, or young Chris talked about serpentinization. The idea being that you serpentinize olivine in these ultramafic rocks, you oxidize the iron, generate hydrogen. And so the early thoughts were that while these fluids are circulating through the crust, you're actually reducing CO2 that's present in the fluid, forming methane. The problem with that is that it's hard to imagine that process occurring over this range of chemical environments and temperatures, resulting in sort of the same fingerprint in terms of the abundances and isotopic composition. Additionally, if you actually look at Lost City, it doesn't contain any CO2 in the fluid because the carbonate solubility is so low. So you can ask yourself, what's the source of carbon? At Von Dam, the CO2 that is present contains radiocarbon, C14. The methane is radiocarbon dead. That signal would have been transferred to the methane had it been produced from the CO2. So the thinking now is that we're sort of moving to a new model that there's actually no methane production while these fluids are circulating through the crust. And what we're actually dealing with is a system where we're actually leaching methane that's trapped in fluid inclusions stored in the rocks. And fluid inclusions are these little vesicles, or they're liquid filled initially. They form when cracks in the olivine heal, trapping fluid containing water and carbon. And then over thousands of years, the actual serpentinization that's producing the hydrogen and the abiotic formation of these hydrocarbons is occurring in these little tiny reaction chambers in the rock. And one of the advantages of this model is that it's fairly well known that reduction of CO2 to methane is sluggish, fairly slow, kinetically inhibited. We have a lot of time to do this. So even if it's a slow rate, it's not zero, it's slow, but it's not zero. You may have thousands of years for this process to occur, unlike the circulation of a fluid through the crust, where the residence time is typically a couple of years in the high temperature reaction zones. And we've analyzed the composition of methane and ethane. This is the isotopic composition. There's a little bit confusing plots here, but down here are the composition of the gases in various rocks, olivine-rich rocks in the crust, and these are the actual vent fluids. And you can see there's pretty good overlap. And similarly for ethane as well, where we could get enough to measure. So isotopically, it appears to be a good match. So what this means is despite these ultramafic vents rich in hydrogen, it's actually not that hydrogen that is, it's a little bit misleading. Where the hydrogen involved with abiotic reduction is decoupled and occurring in a separate reaction chamber over thousands of years. So I want to go to a different system now, so that sort of looks at the occurrence of low molecular weight hydrocarbons in high temperature in the end-member black smoker fluids, and go to processes occurring in perhaps some of these lower temperature mixed fluids. And this is a reaction sequence of a sort of stepwise reduction of CO2 to methane. We've examined this through a series of laboratory experiments. And what these experiments have shown is that this reaction, the production of formic acid from CO2 with hydrogen and ultimately carbon monoxide, this is essentially the water-gas shift reaction in an aqueous environment. It's very fast at elevated temperatures, whereas the subsequent reduction to methanol and eventually methane is sluggish and slow, but it does occur. And I'm going to come back to this later with some experimental data. So you might expect these species to be in equilibrium in hydrothermal vent fluids. If we look at these fluids, so this is a weird way that hydrothermal geochemists look at data. We have this annoying problem that there's a lot of seawater on the seafloor, and every time we go to sample, we typically entrain. What we want is really the end member, the pure fluid that's coming out of the vent. Of course, we never get that. But so we always entrain a little bit during sampling, but there's also mixing that happens below the seafloor with just ambient seawater. Fortunately, the end member fluids have 0 magnesium, so we can actually correct and calculate very carefully how much seawater we've entrained in the fluid. So what we call an end member fluid will plot on the y-axis here at 0 magnesium, and then if you mix in any seawater, you'll get these other sort of mixed fluids that contain significant amounts of fluid. So these are the formate concentrations that this is Van Dam in blue, Picard in red here, and Lost City in green. I didn't plot this with magnesium just because it got too cluttered, but that's the range of concentrations at Lost City. And what you can see is the end member here at Van Dam, for example, is fairly low, but measurable formate. It's in equilibrium with the CO2 and the hydrogen that we measure, but low. And that's what you would predict at the higher temperatures. And then when you mix in seawater, the fluid cools, you get respeciation, reduction of CO2 to form these near millimolar concentrations of formate in the fluid. If you take thermodynamic data for this reaction, we can calculate what we would expect at the conditions that we sampled at based on the hydrogen and the CO2 and the pH that we measure. And all these fluids are very close to thermodynamic equilibrium in the system. And this is just mentioned here. So Van Dam is an ultramafic system. This Picard here, that's a mafic system, salt hosted. We see the same thing. It happens to have fairly high hydrogen. We can see these enrichments in the lower temperature mixed fluids. So this is a great example of abiotic synthesis in these low temperature environments. One of the key points here is that this reaction would not be possible if methane was not kinetically inhibited in forming in real time in these fluids. If the system went to equilibrium, it would all be methane, right? And you wouldn't be able to form these abiotic intermediaries. Another interesting aspect of these fluids, we measured methane thiol in the fluids. And you can see a very strong correlation with formate, suggesting that a similar process might be going on producing methane thiol. These did not achieve thermodynamic equilibrium, but they may have been on their way to getting there. And so it's not concrete, but there is some evidence that we're abiotically producing this interesting sulfur compound. So I want to go back to methane and show some experimental data because sort of put it in the context of what does it take to actually make methane. And the reason I want to do this is there's been a lot of experimental work looking for potential catalysts for this process because of trying to understand it's recognized that it's kinetically inhibited. How do we get around these barriers? This is one experiment that we did looking potentially at formate stability, but also methane and methanol production. The way we do these experiments is we actually, it's kind of a little bit hard to see, but we actually inject or we heat formic acid, which rapidly decomposes to produce CO2 and hydrogen. And then we can look at the reactions involving those two reactants. It's just an easy way experimentally to do the reaction. It looks like the formic acid completely went away here, but actually it's just this is actually the equilibrium concentrations that are just very low that you would expect in this system. But the interesting thing here is that we're looking at methane. We get steady production of methane over time. We also get steady production of methanol in the system. And we're looking at a sort of a conversion efficiency, about 1% of the carbon in the system was converted to methanol. For those of you who are wondering, 2,000 days is about 5 years. So this is a really long experiment. The thing is, though, it's geologically, it's instantaneous. 5 years is nothing in a geologic system. So, and one of the key aspects of this experiment is we did not add a catalyst. There were no minerals in this catalyst. This is a homogeneous reaction occurring in the dissolved phase of the experiment. And so there's been an enormous amount of work looking at catalytic activity. And if you plot the rates of methane production in these systems, so this is the maximum methane production rate against the hydrogen concentration, the biggest correlation, the biggest factor appears to be the concentration of hydrogen. So these experiments in yellow and the white one, yellow circles here, contain no added catalysts. All these other experiments contained purported catalytically active minerals. But you can see the biggest, the most appears to be the most important variable is the dissolved hydrogen concentration. Temperature doesn't appear to be that critical, nor does the actual presence of the catalyst. And some of the fastest rates that we're seeing are with these catalyst-free experiments. So this really emphasizes the importance of time. If we're thinking, you know, those of us who do experiments, we want to see reactions in the lab, but it's important to recognize that geology is not constrained by our ability to do these experiments. So, and this gets to the mechanism. What is the mechanism of these reactions? There's a lot of discussion of Fischer-Tropsch type reactions, or in the case of methane, Sabatier reactions, and what are the catalysts involved. I would argue that at least if you have the time, it's not essential that you actually need a catalyst to make methane in these systems. What am I doing on time? Okay. And then I just want to finish up with one last example. This is a figure from a paper by Menez in 2018, and this is from a serpentinized ultramafic rock in the Atlantis Massif, which underlies the Lost City hydrothermal field. And what they found was this is S-stub micro. I actually don't know what that is, but it's I think it's a Zane. I think it's a Zane's technique, or synchrotron technique. But anyway, the point of this, the reason I put it in is that they documented the occurrence of amino acids associated with iron saponites, clay mineral that formed in these rocks during hydrothermal alteration. And I think they estimated that based on the mineralogy at temperatures of about 200 degrees. And they argued that this is tryptophan and hydroxyanthranilic acid here, that these amino acids were forming abiotically, and that they were by a Friedel-Crafts reaction that was catalyzed by the iron-rich clay in these environments. And the mechanism here, and so they propose that you're abiotically forming perhaps aromatic compounds or heteroaromatic compounds, and you're alkylating, maybe adding a pyruvate group to the initial aromatic structure, and suggested that these are actually abiotic amino acids forming in the crust on Earth. I would argue a more likely scenario, Susan Lang mentioned yesterday, that when you circulate seawater through the crust, the dissolved organic matter goes away. We know there was circulation of seawater through these rocks. So what we might actually be, if their hypothesis for the formation of these compounds is correct, what might actually be going on is that you're thermally altering dissolved organic matter in seawater, providing an organic or heteroaromatic compound that then gets transformed into these amino acids. Now, I view that as a potential abiotic process, but technically that's not an abiotic synthesis because the dissolved organic matter was originally from biogenic material. However, if you had a similar process occurring on an ocean world, it would be abiotic. And you can imagine in a ocean on Enceladus, if you have this massive unconsolidated chondritic carbonaceous material, we know that if you heat that, this is from an experiment by Mark Sefton, if you heat the insoluble solid residue, you generate tons of aromatic compounds. And so in that case, it would be abiotic. And so the point here is that we have this potentially vast inventory of reactants that can participate in those types of reactions to generate new organic compounds. And if you look at the abiotic synthesis literature, there's always a somewhat strict definition of what abiotic synthesis is. It's reduction of CO2 or carbon monoxide to form reduced organic compounds. And I think it would be in our interest to expand that definition to involve abiotic reactants as well. And you can imagine the host of the range of experiments that would need to be done to try and constrain those processes. But these are the types of reactions that are going to be likely occurring on an ocean world where the amount of carbon is enormous. So, one final point is on Earth, just in terms of the amount of compounds that you can generate. On Earth, you can look at petroleum systems, for example, where you have pterogen, and they generate oil over millions of years at very low temperatures, right? So you can imagine perhaps an analogous system occurring on ocean worlds at relatively low temperatures just by thermally maturing this vast quantity of macromolecular material that's potentially available. So I'll finish there and hand it over to Kristen. These are just the take-home points, somewhat simple, but the recognition that single carbon compounds readily react in these systems. Emphasize the importance of time when we're doing experiments and thinking about these systems, and just sort of expanding our view of abiotic synthesis a little bit to consider all these possible reactions that potentially could be going on. So I'll stop there.
Thanks, Jeff. All right, we're going to go right into Kristen's talk, and then afterwards there will be time for discussion of everything we've heard this morning.
Okay, so everybody can hear me? I can hear myself, so that's excellent. Okay, so those our talks from Barbara and Jeff were excellent setups for me to talk about experimental arrangements. So as we all know, life on our planet is filled with signatures that are from those particular organisms. And so it's very difficult to get after the abiotic components that exist in those environments. So this is why I think about experiments quite an awful lot. There's a couple takeaway messages that I wanted to make sure to highlight very distinctly. Abiotic reactions include more than the CO2 as a starting material. Carbon bonds can be formed at hydrothermal conditions. Hydrothermal water can act more like an organic solvent, which can sometimes be forgotten in some of these environments. And the abiotic background is not independent of the mineralogical and inorganic species around it. So for those of you who don't know me very well, I'm an assistant professor at Rensselaer Polytechnic Institute, and my research group is called Penguin, which is a tortured acronym for people exploring nascent geomimicry utilizing investigative networks. And this is the unveiling of a illustration by a sophomore undergraduate in my lab named Molly Drappa. So the first time I've gotten to show it. And essentially what my research group tries to do is explore the mechanistic and kinetic reactions of aqueous organic chemistry on mineral surfaces. So that's done with a series of different kinds of experiments: hydrothermal, electrochemical, which is my most recent obsession, thermodynamic calculations, because it came from the lab of Everett Schock, so you always have to be contaminated with thermodynamics after spending any time with Everett, and analytical chemistry, because any experiment requires that you have a really extensive way to measure that particular product yield. If you can't measure whatever you're doing in the lab, then you're not doing a proper experiment. And some of the work that I've done before, when we've been talking about this abiotic inventory, there's actually a lot of complexity that can arrive even from one starting material. And so doing hydrothermal experiments beginning with one compound, in this case, phenylacetic acid, which was a great target for someone who wanted to graduate on time and a PhD. You start with that in a mineral powder with water, place it in gold capsules. There is no such thing as an inert surface for experiments. You can only find materials that are as inert as you possibly can get for different kinds of compounds of interest. Place that into a cold seal vessel, heat it to 300 degrees Celsius, extract afterwards, and then couple to whatever your favorite analytical technique is. Gas chromatography is really good for kinetic series data for this type of series of compounds. The results of those experiments, at least with phenylacetic acid as a starting material, is that you end up having here on the x-axis time, so a kinetic series, and on the y-axis we have mole percent. If you start with this compound, the dotted line is without any mineral. You can have a 1-to-1 yield, essentially, of the decarboxylation product. When you add minerals, you end up consuming additional products, additional reactant towards additional product pathways, because you can see that you're not enhancing this initial reaction. This is because there ends up being new reaction pathways available because of the availability of this mineral surface. And so you can see that we have a carbon-carbon bond forming in a dibenzyl ketone, and also transstilbene being in a fairly large abundance. This is the product pathway map that you would generate for that kind of reaction. And this is what the kind of information you can get from very careful kinetic studies. And so in this case, going from our starting material, you can go down the path of a dibenzyl ketone. Ziming Yang did an exhaustive amount of work with dibenzyl ketone, which gets ugly, and lots of additional carbon-carbon bonds end up being formed from that amount. Because there's radical formation, you can end up with this bibenzyl, and bibenzyl can go to transstilbene, and so on and so on. Thermodynamic calculations end up being very helpful in the formation of some of these experimental studies. As anybody knows who does modeling, modeling only gives you directionality. It gives you absolutely no information about the kinetics, which is why the experimental complement ends up being very helpful. So in this case, this reaction of decarboxylation using a proxy molecule, acetic acid, for both components of the decarboxylation and the ketone formation. You can see that there ends up being in this, the axes being temperature on the x and log K on the y. A reminder for everybody what K stands for, and this is, I cover this in my quantitative analysis class with my undergrads. So favorability being a rot term, you're just saying that there is more product yield in this situation where it's above zero. Decarboxylation is something that seems like it can occur across a range of temperatures, but there's a temperature dependence for some of this carbon-carbon bond formation. So depending on the kind of environment you find yourself in, you may be able to produce certain compounds, or you may not. And that's something that thermodynamics coupled with experimental procedures gives us information about. When the mineral magnetite is present in these experimental mixtures, there ends up being more yield, in addition to the dibenzyl ketone transstilbene, down these additional product paths to form benzoic acid, deoxybenzoin, and benzene. I include this type of plot because benzoic acid here, you can see that it actually starts to grow in, and then it's very clearly consumed during that reaction. So there ends up being these interplays between molecules as they're being formed, and then they're being consumed down additional product pathways. So the full map, at least for this work, published in 2021, is that you can go down, more than one path from your starting material, and that once that starting material exists and those additional products exist, you can end up with secondary and tertiary products. And so your reaction web goes from something that was very simple to very complex very quickly. So what Jeff just showed us with the overall amount of molecules that come from, say, meteoritic material, you can end up with a multitude of different kinds of reaction paths that can occur. And depending on what else is present in your solution, you can go off in lots of different directions. Simplified down, conventional wisdom for a long time was that hydrothermal conditions only serves to break things down. In reality, depending on the rest of the constituents around your system, you can actually make carbon bonds and go down additional product pathways. It's not only a mechanism by which you're breaking things apart. Okay. So I get a little obsessed with pathway maps, and it's because it's a really lovely way to just think about reaction networks. Biochemists already think in reaction maps, and there's lots of fantastic work on metabolites and precursors in each one of these systems. Here I zoom in on one of our favorites, the citric acid cycle in the prebiotic literature. And it's the reason I do is because I lived in Tokyo, Japan for 4 years, and the Tokyo metro map looks a lot like the citric acid cycle. The Yamanote line is central to your life in Tokyo. And so when we're thinking about these fabulous maps interconverting between different kinds of organic molecules and how you can go from one location to another, depending on your transfer in the line, can we do the same thing with abiotic reactions? Yes, but it's a lot of work, but that's okay. I've got a whole career. So in this example, these are abiotic reactions that were observed experimentally. It is a reimagining of some of the reactions covered in this riveting chapter, Earth is Organic Chemist, in the Deep Carbon book from the Deep Carbon Observatory. In this approach, this is work by many workers, many of which who came through Everett Chalk's group in the Hydrothermal Organic Geochemistry division, showing you that depending on where you start, you can go off in different kinds of directions, and you can also end up in locations where maybe you're going to stop unless you have some other reversible process at play. I talk a lot with geologists, and so you have to be careful. You're putting too many organic reactions in those environments, and that's why I actually really love conversations in the workshop here. People are not allergic to carbon-carbon bonds, which is really exciting for me. And so I think about this in the Yamanote, in the Tokyo Metro map sort of perspective, is that there are going to be, in certain environments, centralized molecules where you can go off in lots of different directions. And then there'll be places that you might have as your final stop. There'll be locations that we don't yet know if they exist. And so during a thermodynamic prediction would be very helpful to understand what could be possible. And then we can do experiments to then make that line more solid. And it's just at least at a starting metric, a good way to think about these different kinds of experimental conditions. It requires a lot of friendly, lovely collaboration to actually get this type of mapping underway. I'm happy to have as many people doing experiments as possible. And if you want to talk to me exhaustively about experiments, I'm here till tomorrow. So different approaches to sorting through organic chemistry on Earth. This session said the Earth perspective. And I just so happen to think that it would be remiss not to talk about the Deep Carbon Observatory while we're here at Carnegie. And so for those of you who are early career people, often during some of these workshops, you end up with these opportunities that you don't necessarily imagine you'll have. And so at a workshop for the Deep Carbon Observatory in St. Andrews, Scotland in 2017, midway through a workshop, they were like, okay, so there is this premise we want to do, the Earth in 5 reactions. You are representing all of organic chemistry. What is the one reaction you think the Earth needs for organic reactions? Well, I'm not stingy, so I gave them 3. And, and so I decided that of the reactions that were possible, decarboxylation, probably because I was working on my PhD in that reaction, oxidation, and aromatization were 3 that I could imagine being very helpful, at least thinking about abiotic reactions and thermogenic or transformation of a biological material on our planet. And then also, of course, mineral facilitated pathways. But something I will point out in terms of experimental work is that we do not yet fully understand everything that can happen in an abiotic context experimentally. There's just a ton of parameter space we need to cover. And so I always refer to it to my students as I'm like, we're in the wild west of understanding exactly what kinds of organic reactions can be done in these abiotic environments. So the Earth in 5 reactions culminated into another workshop where a room of like some of which are people who are here were in the Carnegie Institute of Science building downtown, being very confused about how to define the most important 5 reactions for our planet. We eventually came up with a consensus, and this is what that diagram looks like, made by Josh Wood, which is that hydrogenation, carboxylation, CO2 dissolution, hydration, and carbonation being the 5 that we agreed upon, and then a couple honorable mentions that became their own papers afterwards for that. At the time, I remember thinking that this was an incredibly ambitious question, but I've grown to appreciate it a great deal more now that I think about what kind of reactions the Earth allows, and then by extension, what kind of reactions these planetary objects and these worlds and icy moons could possibly allow with different kinds of parameters. So for the deep carbon cycle through 5 reactions paper, if you want to find the papers, and I have a couple of screenshots here, they're from the American Mineralogist 2019-2020, volumes 104 and 105. This one in particular, they described about how the Earth in 5 reactions came to be and the reactions that by ballot and discussion in different kinds of workshops were agreed upon. So we've got our hydrogenation, our carboxylation, our carbonation, and carbon dioxide dissociation, outgassing. It's important to note that in each of these papers, they do not separate like this paper is entirely abiotic, this paper is entirely biogenic. It is a mix. And that's because it's really hard to separate on our own planet the difference between biogenic and abiotic sources. And in fact, it would be argued that from the prebiotic sense, if something was really successful as an abiotic process, then life, because of energetics, utilized that pathway to then become what we refer to as life today. At least that's one of the perspectives we usually have in the prebiotic community. So Earth in 5 reactions grappling with meaning and value in science, because the question is what's the most important and how do you define that? So Bob Azin did that related to the workshop. Carbonation, the Urey reaction, deep Earth carbon reactions through time and space. Some of the papers that I got on, which were Let There Be Water, How Hydration and Dehydration Reactions Accompany Key Earth and Life Processes, Abiotic and Biotic Processes that Drive Carboxylation and Decarboxylation Reactions, Hydrogenation Reactions of Carbon on Earth, Linking Methane, Margarine, and Life, Carbonation and Decarbonation Reactions, Implications for Planetary Habitability. This all seemed to me very topical for the type of discussion we're trying to have this week. So a slide that I have been beating on at most conferences for a while is that to differentiate signs of life, you must understand what is possible without life. And to do that, you need to do abiotic experiments because, as Barbara and Jeff have both pointed out, it is very hard to measure abiotic processes in an environment that has a lot of biology going on. So hydrothermal vents, as a starting environment, already has a lot of chemical parameter space variability between it. And so if you're trying to look for individual parameters for an experiment, you have to think about the fact that these particular vent features are results of different processes, results of different chemistries, and have sometimes mixed environments depending on what else is there. Also, we don't want to be remiss of our friend thermodynamics. When you're thinking about the Gibbs energy for any given reaction, the T term ends up being very important for some of these different kinds of reactions. And so as our temperature is increasing, the entropy ends up being a bit more important. Oh. And as I usually show in my quantitative analysis class, this is in fact a table directly pinched from the Harris quantitative analysis textbook. The properties for water, in this case Kw, the autoprotolysis of water, which I'd never heard said out loud this way until I was teaching quantitative analysis. You end up having the separation into protons and hydroxides actually having a different K value depending on the temperature that you're going after it. So you can see this here, the same data in this plot, and that it's a little bit different for deuterium enriched water as well. This also results in the fact that high temperature water can have properties that is more akin to organic solvents. So certain kinds of reactions that you would not imagine to be possible at conditions at, say, room temperature or 2 degrees C in seawater now become a little bit more viable because you're talking about doing a reaction in essentially acetone or methylene chloride. So dielectric constants, of course, is the ability to basically to like to dissolve like. And so organic molecules are much more soluble at a high temperature. That's being demonstrated here with temperature on the x-axis and log K on the y. So it's such a molecule such as toluene ends up being a bit more soluble once you're getting to 300 degrees C versus whenever it's at lower temperature. Speaking of experimental pathways and reactions, Jeff's work, as well as Tom McCollum, have worked after these types of reaction pathways that can go from long chain carboxylic acids down to smaller chain carboxylic acids at hydrothermal conditions using different kinds of mineral buffers. And this is then summarized as going from, say, an alkane to an alkene, an alcohol, a ketone, carboxylic acid, and alkane, and back again. When I did the experiments with minerals, I found that there was a little bit different approach to this. And so at least with these kind of compounds, these ones specifically being in the study, but these being analogs for what's described here, Yang and Glein saw that there was, of course, this reaction for decarboxylation, and there was this possible, ketone deterioration versus experiments down to toluene. But when trying to think about some of these other oxide minerals, I did not necessarily see the formation of the carboxylic acids from the ketone. Instead, there ends up being this pathway to the ketones from the carboxylic acid itself. And so the mineral presence actually starts to alter the paths that you think are available. And so doing experiments with and without other inorganic constituents becomes important to understand everything that's possible. I teach a class called Hydrothermal Experimental Methods, where I really get into the nitty-gritty details about how we try to make hydrothermal experimental setups. They are expensive and require some different safety considerations. Seawald's work deals a lot with gold bag reactors. In this case, this is a setup that is in Jamstec, Yokosuka, Japan. And so this is a reaction setup where a gold bag is filled with your reaction mixture of interest, pressurized, and then placed into this heating mantle so that you can operate an experiment where you can systematically sample throughout. You have to, at certain times, if you want to continue the experiment, you have to actually reintroduce solution and then continue. And so as an approach, it's good for small molecule soluble species, but may not be good for things that are larger and less soluble. So depending on what kind of experimental direction you want to take, different kinds of setups are not equal to one another. You have to pick the one that's going to be good for your application. A documentary that I would strongly recommend if you want to get sort of the prebiotic chemistry perspective from at least the 1990s, where people were really fighting amongst each other, it would be Life is Impossible. In here, Remy Hennett talks about some of the hydrothermal experiments that were being performed trying to go after prebiotic reactions. And hydrothermal reactions take many different forms, including cold seal vessel experiments, which is something that I'm very well acquainted with and something I'm building at RPI. So in this example, especially for different techniques, I always tell my students sometimes that the experimental technique that you're interested in using may not be obviously titled, experimental technique X for use in Y. It's the Williams paper from 2001 is talking about borate in different kinds of mineralogical information. It's the only place that this particular setup is published. So depending on what you want to do, you either want to make friends with an experimentalist, I'm available, or you can look at different kinds of literature, seeing what kind of goals they had in mind. The reason I bring up the cold seal vessel is because in addition to thinking about abiotic reactions and prebiotic reactions, this was actually the technique that was used for trying to go after meteorite abundance heating IOM. So this was an experiment done by Linda Williams and Sandra Pizzarello at ASU in the same reactor bay that I was using, where essentially they took R-type carbonaceous chondrite materials and heated the IOM to show what kinds of products you could get from that heating. And what they found was that there was, from the IOM, quite a lot of ammonia. And so if you heat this product, you can end up with a screaming amount of ammonia that's available now for any kinds of reactions that you want to do next from this initial starting material. And so in this case, the carbonaceous chondrites are, of course, an array of different kinds of compounds. And so there's amino acids, ammonia, amines, aldehydes and ketones, hydroxyl acids, hydrocarbons, and carboxylic acids in different kinds of abundances and often with a lot of different kinds of aromaticity. Something to note, and I'm sure we'll hear about more of it today with the astromaterials section, is that depending on our information from meteorite material is dependent on who is doing the analysis at the time. There are people who specialize in the IOM, there are people who specialize in the soluble organic matter, there are people who specialize in different kinds of fractions. So when you think about the starting materials from any particular meteorite, you want to actually take into account lots of different researchers so that you can know what one type of meteorite is providing for you, rather than just assuming that maybe there's only this insoluble organic matter or this soluble organic matter. Speaking of experiments, you don't have to do all experiments in the really fancy, expensive setups. There are experiments you can do as well in serum vials. This is just one of several studies from the Barge group that does exactly that. In this case, starting from pyruvic acid and glycolic acid and going off in different directions based off of pH gradients that were being applied to the system with different kinds of minerals that were present. You could also do experiments in quartz tubes. Emma Brown, who has a poster here, would be one of the people to talk to about that technique. So this is actually quartz tubes being a misnomer. It's silicon dioxide glass, which is supposed to be free of the borate, which could be a possible catalyst in some sort of organic reactions. So if you do this experimental setup, in this case, research is showing that you can put this on a vacuum line and then seal the tube. You can place those glass tubes into an oven, the caveat being that the experiments will contain a headspace. So if you care about doing experiments where there is absolutely no headspace, just be careful that whatever you're trying to go after won't be something that will equilibrate between the headspace and the liquid phase. Just because one of my favorite things to talk about now is electrochemistry. I also want to point out that there, at least at hydrothermal environments on our own planet, there has been observations that there is electrochemical gradients being observed, often because of the temperature difference between the internal temperature of the vent and the external seawater. And so this is an energy source I could imagine existing on some of these ocean worlds that we're looking at as another place to start reactions. I could go on and on, but I won't, about different kinds of flow-through reactors and other types of reaction setups that exist. This is one that's from some colleagues of mine in Japan that was with the purpose of going after electrochemical deposition in a flow-through system, doing electrochemistry in situ up to 100 degrees, 150 degrees C in a peak-lined vessel. This is the kind of setup that could be available for reactions if you want to do some flow-through types of design. Here's another paper with a titanium vessel that can do flow-through reactions attached to an ESCO pump, so a pump that's very well calibrated for different kinds of pressure. So it's another reaction system that could be available. This one is from a paper by Imai, where it's talking about designing a flow-through reactor system to model exactly a hydrothermal vent. And so there is a heated zone and there's a cooling zone. And the purpose of their experiment was actually to go and make elongated peptides. And so the idea is that after going through your reaction system, you are making a slightly larger peptide structure, you're cooling it down again, and you're making it go again so that you can continue to elongate the peptide in this abiotic hydrothermal synthesis. And improvements upon that experimental design. This paper is mostly in Japanese, but you can actually get it, and the captions are in English, so you can take a look. And then from the prebiotic sense, there's also a lot of work in microfluidics that's starting to come about. And so microfluidics allows us to go after individual components, in this case, starting with, say, CO2 and hydrogen, going to these different kinds of prebiotic relevant molecules. And so our array of different kinds of experiments is of course available, and just make friends with people who have the setups and you can move forward on understanding more of these abiotic reactions. So takeaway messages again, what I've said before, and also that experiments can help because it's really difficult for us to analyze our biologically, contaminated system around us and understand exactly what's possible unless we do some experiments to help along the way. Okay, so that's it for me. So thank you very much.
All right, well, we started a few minutes late this morning with the talks, so we'll obviously have we still have time for questions, for discussion, and we'll open it up discussion for everybody, all of the talks this morning. So any questions people have.
Would it make sense to 5 minute break for everyone?
Well, immediately after this is a break. So if we take 10 minutes, then we have like a 20-minute break, is that? Or do people prefer we take a break and then come back?
Can we do the break now and then start,
Because then, yeah, everyone's pressure.
have the discussion when the break was supposed to be?
Yeah, I suppose we could do that. Sure.
Huh?
Yeah, we could do some of that too. All right, yeah, if that's what people would prefer. Sure, yeah, let's have one online question. You need a microphone though.
Give it to you.
Okay. All right, to say, okay, it looks like this question, all right, it says, when doing the hydrothermal reactions with magnetite and hematite, do you notice any difference in the electron transfer and overall reaction given the mixed oxidation states found within magnetite, iron 2 and 3? This is from Samuel Arnold from UAH, an undergraduate.
That's one of the reasons I started to obsess about electrochemistry, was because of noticing an actual redox reaction that I couldn't pursue in situ in the hydrothermal experiment. So magnetite actually has the ability to perform redox reactions, either by being consumed or possibly as a semiconductor. So yeah, this was something that started to observe with the hydrothermal experiments.
Okay. Did you have a question?
Well, I'm confused about what we're doing at first.
Yeah.
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 Well, hang on. Yeah, good question. So
We have a break. I'm
What-
looking at the thing here, 10 a.m.
right, we're supposed to have a break at 10, but we didn't start with the talks until about 8:15, which was 15 minutes later. So I wanted to make sure there was time for discussion of the talks we just had.
Okay.
So I thought we could eat in like about 10 minutes into the break and then do that. Or we could take a quick break and come back, because we need to start the next session in order to keep on time with the photo and lunch and everything else this afternoon.
It sounds like people want a break, so maybe we should take a break
Yeah,
now.
let's take a break.
Yeah.
But we'll come back at 10:20. We'll be back in here at 10:20.